All right, so we start our first topic here in chapter 13. Again, if we're thinking about chemistry and chemical reactions, our first topic that we're going to go over is the idea of kinetics. Now, chemical kinetics is not a terribly difficult concept in terms of what it is, but the calculations that we're going to be getting into are going to be a little bit more rigorous as we go. So let's start off with a simple definition. What is kinetics? So in particular, kinetics is an area of chemistry where we are really concerned about the rates of reaction, or a better way of thinking about that is reaction speed. So what governs whether a reaction is going to be fast or slow? And as it turns out, there are a lot of different things that can govern whether a reaction is fast or slow. And so really in this chapter, what we're going to get into are looking at all of those different things, and then looking at how to determine just how fast a reaction goes through a variety of methods. And in particular, we're going to focus mostly on concentration, because that is the one factor that we probably have the most direct impact over. I can make a solution that is 2 molar, or I can make a solution that is 0.1 molar. I have the ability to kind of change that fluidly. With things like temperature, yeah, I can change the temperature of the reaction, but within a certain range of allowables. I can change other factors as well, depending upon whether or not I have access to them. But overall, those are the things that we're going to be looking for. And so your first interactive question is going to be this. I've already mentioned a couple of factors of reaction and how they will proceed fast or slow. What I want you to do is this. Reply to the discussion board here. What are some things that would impact how quickly or slowly a reaction would proceed? I already mentioned temperature and concentration. Are there others that you can think of that might make a difference in terms of how fast or how slow a reaction goes? Go ahead and try. All right, so we've got some good thoughts here. Things like catalysis, or maybe it has something to do with electronegativity. Maybe it has something to do with pressure and volume. Maybe it has something to do with surface area or the state of the reactants themselves. And when it comes down to it, there are 5 main factors that we can look at. The 5 factors that we can look at are the physical phase of the reactants themselves. So are we dealing with solids, liquids, or gases, or solutions? The concentration that they are. Obviously, the more concentrated they are, the more reacting species there is, more likely it is that the reaction is going to go faster. We also need to look at things like temperature. One of you said something along the lines of surface area. That's going to be really, really important, especially if we are dealing with non-solution, non-liquid kind of substances. And then catalysts, which we'll get into in much greater detail as we go. But before we really get into all of those different factors, it's probably really important for us to just have a really good understanding of what actually happens when a chemical reaction takes place. Because if we don't understand conceptually what is going on when a reaction happens, it's going to be really hard to kind of visualize how these individual factors make a difference. And so from Chem 105, we know that bonds are broken and new bonds form. We knew that all along, right? Got to break up the old stuff and get it to rearrange to make the new stuff. But how does that actually work? Well, the bonds don't just break on their own. We know that it requires energy. Where does that energy come from? Well, the energy comes mainly from its own internal energy, the temperature that it's at naturally, plus whatever energy it gets as it interacts with the other stuff. And so to get that other energy, we have to look into collisions. So in order for a chemical reaction to occur, in order for those bonds to break, we've got to see these molecules colliding with each other. That's going to get them close enough to break the existing bonds and to reform new bonds all in that same moment of collision. But in order for that to happen, the collisions can't just happen any old way. They have to have two other factors associated with them. They have to have a proper orientation. That means that they have to be positioned in the correct three-dimensional way so that whatever it is that is going to interact actually interacts. And there has to be enough energy in the collision to actually cause those bonds to break in the first place. It's a simplistic example, but let me attempt to illustrate. Let's say that the whole purpose of this reaction is to get these two markers to come together. Simple enough idea, right? Well, I can't get the two markers to come together if they never actually interact. So there's your collision. Now, to get them to stick into each other, they actually have to be oriented correctly. I can't have both marker heads facing each other. I can't have both marker backs facing each other. I have to have one end and one back. There's the proper orientation. And as far as energy is concerned, if I don't push hard enough, even if I have the correct orientation, I can't get the markers to actually connect. But with the proper energy, they go together. So all three factors have to be there. They have to interact. They have to interact correctly. And they have to interact with enough energy to reorient all the bonds that need to be reoriented. Without one of those three, the reaction doesn't occur. Now, formally, we refer to this idea of chemical reactions by collision as the collision model of the reaction. And if I look at the collision model of the reaction, I can see that the products of the reaction are supposed to be these two green dots, let's call them chlorine, and this red and blue dot here, we're going to call that, it looks like nitrogen monoxide, NO. So beforehand, we had a chlorine atom, and we had a molecule of NaCl. The idea is we're supposed to get chlorine gas, Cl2, and nitrogen monoxide. So that's our chemical reaction here. Now notice the difference between the two. In the top one, our chlorines end up colliding with each other. And if there's enough energy in that collision, that chlorine colliding with the other chlorine provides enough energy to break off the chlorine from the NaCl and attach it to the other chlorine atom. But if that chlorine comes at it from the other side and collides with the oxygen instead of the other chlorine, even if we hit it with tons of energy, energy itself is not sufficient for the chemical reaction. And we need to have all three: energy, orientation, with the collision. Collision on its own, not good enough. Collision with orientation, not good enough if there's not enough energy. Collision with energy, not good enough if the orientation is poor. We've got to have all three. That's what's going to make the chemical reaction go. As far as energy is concerned, this is where we have to introduce a term here. This is activation energy. Activation energy is the minimum energy that is required to initiate a chemical reaction. Best way to kind of describe it is it's that minimum amount of energy that you need to get that collision to occur with enough energy. Now, we will talk in greater detail as this chapter goes on about how chemical reactions are usually multi-step affairs, how a chemical reaction usually takes place over a number of small steps instead of in one large one. That's called a reaction mechanism. And activation energy is at the heart of what makes a reaction slow or fast from an energy standpoint. The higher that activation energy is, more energy input is required, the slower that reaction is going to be at a given temperature. Because if you can't get over that barrier, you can't have a reaction. So think about it as, if you like to golf, think about it as going over a hill. If you've never golfed before in your life, or if you're terrible at it like I am, think about your worst nightmare mini golf course. The one hill where the hole's just at the top, and it's just a giant 4-foot hill or something like that. And you sit there and you whack at it, and it goes, doesn't quite make it. It rolls all the way back down and into the parking lot. That's activation energy. If you don't put enough energy into that golf ball to get it to the top of the hill, it rolls all the way back down to where you started. So that's what we need to look at. That's what we need to think about as far as a reaction is concerned. We've got to climb that hill. We got to get over that hump. If we don't get over that hump, the reaction isn't going to happen. All right, another factor here is the physical state of reactants. Now, we're going to introduce some more terminology here. The overarching idea, though, is relatively simple. Some phases of matter are more likely to interact than others. And it's all about the mobility of the phase. Gas phase reactions are the most easy to react because those molecules are all in constant random motion. They completely fill up the space that they're in. Liquids, it's a little bit better. It's not as good, but it's not terrible either. Those molecules at least are able to move about a little bit inside of that liquid or inside of that solution. Solid phase, it's pretty tough. Those molecules are bound to their positions because of the packed nature of those solids. And so we can kind of put it into terms. If I have a homogeneous reaction where I've got all the reactants all in the same phase, they're all in the gas phase, they're all in the liquid phase or in solution, those reactions usually can go faster because they're all in the same phase. They can all mingle together relatively easily. Solids, if you have a solid state homogeneous reaction, it's going to be a little bit difficult to do just because of the mobility issue. You're also going to run into the problems of there's just not that many solid phase reactions that are just solid phase. For heterogeneous, we have reactants in different phases. There can be some interaction issues. If I have, for example, a catalytic converter in my car, solid piece of metal inside of my exhaust system, I'm trying to get the reaction to occur on that solid piece of metal to turn the exhaust fumes into less dangerous exhaust fumes. There's going to be an issue if the catalytic converter is the size of a quarter. In those circumstances, surface area is what we need to work with. That's why a catalytic converter, it's not a little piece of metal that's really thick. It's a long, thin sheet of metal where lots of reaction can occur simultaneously to maximize the capability of getting that extra oxygen into those exhaust fumes to turn them into less dangerous gases. So generally speaking, again, this is usually, we're talking about solids or liquids here, increasing the surface area is the most easy way to increase the rate of those reactions. Now, in some cases, even with maximum surface area, we're still going to run into problems. Some reactions are just naturally slow. But if we're talking about, can I use 3 grams of aluminum powder or a 3-gram piece of aluminum foil? Well, the aluminum powder is going to be the way to go. Powder has way more surface area than the foil does. I'm going to take a 3-gram aluminum foil over a 3-gram stick. And I'm going to take the foil. It's got more surface area. If I have a liquid, spreading it over a large surface area, a wide pan, as opposed to a narrow cup, would make a big difference in terms of reactivity. You know, think about it. If you're going to burn alcohol for whatever reason, laying it out flat in a large dish is going to burn off that alcohol way faster than if it's in a tiny tube. So surface area makes a big difference in those kinds of circumstances. We can also look at reactant concentration. Now, we're going to spend a good bit of tomorrow focusing very much so on reactant concentration. But just a general idea, we can have an illustration here. Reactions are going to go faster when we have more reactants. That's the general concept here. So in both of these cases, we are burning steel wool. You've ever burned steel wool in a flame? It kind of looks like that. It just kind of glows, gets a little bit dark and kind of flaky, doesn't really ignite like we think of ignition. Most people look at that and actually think that the steel wool is melting. It's actually not. It's actually going through more or less a flameless combustion. Now, the difference between this picture and this one is the environment. This is being done in open air. Top picture here, open air, 20% oxygen, give or take a little bit. Here, we have a flask of pure oxygen. And in that pure oxygen environment, now we've got a lot more surface area, we've got a greater concentration. Reaction goes a lot more vigorously, looks a lot more like a firework as opposed to just something kind of getting hot. So yes, concentration does have a significant impact. It does make a pretty considerable difference. And again, we'll get more into that when we talk about rate laws tomorrow. Temperature. Now, in the model of our collision theory, we can understand this idea of temperature pretty well. If activation energy is a certain level, raising the internal energy of the reactants by raising their temperature is going to make that activation energy a little bit more attainable. And so naturally, as a result, increasing temperature usually results in an increase in reaction rate as well. General rule of thumb for temperature is this. For every 10-degree increase in temperature, we see a rough doubling in reaction speed. When we look at our lab for tomorrow afternoon we're doing our first kinetics lab. And this is one of the things that we will be looking at very closely in that lab tomorrow afternoon, is we're looking at a variety of factors. But one of them will be, does this rule of thumb actually hold up? And with that said, let's go ahead and take a break here. And we will start with reaction rates and looking at relative rates of reaction after the break here. So